a specialized thing in real time you do when you have no interrupts. I mean, we come to this later. Okay. A task has, of course, a priority. Everything is based on this priority. It's not like the Linux nice level. It serves a similar function, but the priority is a criteria if a task gets scheduled or not. It has some states, of course. Most important ones are blocked, ready, and running. And it's maintained by the real-time kernel. So basically a task is an endless loop. It blocks if it wants something from outside, I/O. Yeah, it's set up by an init function. In case of RTI, you insert the kernel module. This is the start of life of a real-time task. And it's made of you see the task is made of disk data. This is the data segment, the code, the stack, and some real-time operating system internal task control block. Of course, what's in this task control block? Most of the time there is, of course, the ID of the task, sometimes the priority, but it's mainly business of the real-time operating system, what's inside. Okay, let's go to scheduling. As I've said before, a task can be preemptive or non-preemptive. And periodic or not periodic. Periodic tasks, as you see in this picture, gets involved every 5th time slice. This is a little bit, this is a little bit simpler than it actually is, but I think it explains the picture. Periodic task, like I've said time sliced before, you see the periodic task gets involved every time the time is over, and so it interrupts the preemptive task, runs a little bit, and then gives back control to the preemptive task. So as we see around 10, there is another high priority non-preemptive task. Yeah. And the periodic task therefore gets involved a little bit later. Depending on the timeline, this is a good or a bad thing. So the interrupt service routine is one of the core concepts, one of the important concepts of a real-time system, because basically it's the function where you get control out of order, which means an interrupt occurs, you can react to it, or the real-time system can decide to ignore it. But the interrupt service routine is a very small part which just looks which interrupt happened, what's the current state of the system, will it return to the task after the interrupt, and well, what priority is the task currently running, and then decide what to do next. So, in case of real time, we have a task, we have an interrupt service routine. Okay, now we are able to react on external events. We have the possibility to activate or deactivate the task, but right now it's a little bit boring because we have no way of communication, we have no way of synchronization. So this is where the message queues comes in, and message queues are for inter-task communication. Usually, in real time, you're using fixed length data. Usually in real time, you do as much as possible at design time. This has a reason, because you want to get this system deterministic. The more you know at design time, the better it will actually go. So fixed length, it sounds like, so real time is really, you must know what you're doing.
In wenigen Minuten wird der Gewinner der Fotoausstellung am Wikipedia-Stand bekannt gegeben. Vielen Dank.
Okay. So in a few minutes we will have a winner for what? Okay, so the message queues. In Artile Linux, we have every flavor of message queues you want. We have mailboxes, we have queues and pipes. In other systems, like Pesos is an embedded real-time system mainly used in consumer environments like DVD players. Probably you have one at your home. But common to all this implementation is you have a maximum size of elements which can be queued, and you can use this message queue for sending data. So, but so I'm wanting to sending data to the screen. Well, in this example, you see two tasks. One simple, something nice to display to the user, but the results aren't that nice because they each get a little time slice, and well, that won't work. So we need more than message queues, we need semaphores. Semaphores is a principle, it's like a token. In the history, on railway tracks, there were, on parts of the railway tracks, there were only one railway. So how to, and telegraphic communications wasn't that good at this time. So they had the problem how to not to crash two trains into each other on this single line. And of course this was easy. They used the token. At the last station, before it went to one line, there was a stop, and either the officer had the token there, and the token was given to the train operator, and with the token, the train operator crossed this part of the railway, or he has to wait until the token arrives. So you are passing tokens. As soon as you have the token, you are allowed to use one device, or whatever you want to use. So here is our token, and task 1 and task 2 in this example both want to get the token. Well, task 1 is in this case faster. Task 2 gets a message, well, your token is not available, and it blocks. So task 1 prints hello world. Task 1 gives this token back and unblocks task 2, which can then print good evening. And then, of course, like every good program, it must give the semaphore back. So semaphores are used for inter-task control communication. You can protect your resources with it. Depending on the implementation, there are counted semaphores. There are some, I think I can imagine some examples where counted semaphores are useful. Most of the times you don't need it. If you want to take a semaphore and you're out of luck, this will block your real-time task. Of course, you have to give it back. Sometimes in case of inter-task control communication, you are speaking of mutexes. Basically, it's a semaphore. It's just it's slightly different, but in this case, it's the same. So, okay, what else do we have to have a working real-time operating system? Of course, we need a timer. Single shot events or periodic events. Sometimes the timer is the only interrupt which is allowed in a real-time system. Then you're doing something from top button. You say, I don't care about hardware interrupts. I don't care about whatever device wants my attention. I just use a periodic timer, and this is my only source of interrupt. And this is time triggered, as I've mentioned before. And in case you know exactly at what time you must react or not, it may be a clever solution than having hardware interrupts, because it's not a matter of how quick or how efficient your processor is used. Yeah, also real-time programming doesn't mean you're using your processor efficiently. It's not, I mean, yeah, you should do with the processor what you want, and you should have sufficient power to do it. But real-time systems, most of the times, is designed to be utilized not more than 70%, and it will be utilized at 70%, even if it does nothing, almost nothing. The rest of like the 30%, are only for unexpected, non-deterministic behavior, especially if you try to make real-time on a architecture like the x86. You need quite a lot of buffer because it's quite non-deterministic. So the timer is one of the most important devices when it's going to go about real time. It's used for delaying, it's used for waiting.